Topic is Pinacol-Pinacolone rearrangement. In this rearrangement, Pinacol converts to Pinacolone. Here we are going to study mechanism of this rearrangement. First, we need to understand what is Pinacol. Pinacol means carbon, adjacent carbon bearing hydroxyl group. Two hydroxyl groups on adjacent carbon, and this converts to pinacolone, ketone or aldehyde. If here is any other carbon, any group, say CH3, then it becomes this way. This molecule becomes ketone, pinacolone, or if it is having hydrogen, then it will convert to aldehyde, pinacolone. Sorry, this is aldehydic group. So point is that in this reaction, pinacol converts to its derivative aldehyde and ketone. So we will going to study actually how this reaction happens. We will take one example. In this example, we will take this molecule CH3, C, CH3, then here OH and OH, here CH3 and CH3. Okay, now we will give numbering to it: 1, 2, 3, 4. Now this is butane, 1, 2, 3, 4, and 2 and 3 position there are hydroxyl group. This is glycol, diglycol, or you can call it pinacol, because on adjacent carbon 2 OH groups are there. So this is pinacol. Ol means alcohol, olone, pinacolone means ketone. Now the thing is that in this reaction we have to use acids. So we have to see how this acid is responsible to start this rearrangement, and how the product is formed. So first step is, say we are using H2SO4 as an acid, and H2SO4 is we call acid because it produces H plus, hydrogen devoid of electron, we call it proton as well. Now this H plus, when is generated, then because this is H plus, so it is requiring electron, and this oxygen bears lone pair of electron. Okay, 2 lone pair of electron, oxygen. Now the point is that oxygen having lone pair of electron, it can donate electron, can form a bond with H plus. Now the point is that this H plus will bind to any of hydroxyl group. Now which hydroxyl group this H plus will bind is depend upon the availability of electron. No doubt here this is oxygen, this is also oxygen, electron available, we may think that same, but it is mostly depend upon this carbon, because this carbon, here you see this carbon is connected with this methyl, and if we see this oxygen, again the same is the situation, methyl and methyl. So availability of electron on this oxygen and on this oxygen is similar, they are similar. So this H plus can combine, or this lone pair of electron can attack to this H plus, and this H plus will get attached to this one of these, either of these oxygen, because both are equal. The situation changes if, say, one of the group is different, or any group is different attached to this carbons. Now in this case, even though here is methyl and chlorine, only one group here, it is different, but we know that chlorine is electronegative group, so it will pull electron toward itself more, so less electron is available on this carbon. So therefore this carbon will pull electron from this oxygen. So availability of electron on the oxygen is less as compared to this oxygen. Therefore this H plus will get attached to this oxygen, not to this. I'm telling the reason. The reason is that availability of electron. If all the groups, these four groups are same, availability of electron on the both oxygen becomes equal, and therefore this H plus can combine to any one oxygen. But in case when the group or groups are different, like in this case, the availability of electron changes. Here less availability as compared to this oxygen because of pooling of electrons, because of electronegative atom. Reverse may happens if there is electron donating group like phenol or something, ester electron donating group, then the more electron will be available here and this hydrogen will be combined here. So point is that in this case, both are equal, so H plus will be attacked by any of oxygen. We will take this oxygen, this will attack on this H plus, and next step is as it is CCS3, then CS3 OH, here OH, and this hydrogen attached, so this H. Now in this case, this molecule here hydrogen attached, so this oxygen will have plus charge, because if you see the valency of oxygen here, it is 3, so plus charge, it has given its lone pair of electron to this bonding, so it will be a plus charge. Now this molecule is unstable, so this molecule try to stabilize. How it is possible? It is possible by breaking the bond. Which bond? The bond will be broken. This bond will be broken and electron will be taken by oxygen, and if you see this, what it is HOH, H2O. The water is forming, and here because electron is taken from this bond by this oxygen, so this carbon will be a plus charge, because electron which is shared between this oxygen and carbon, both electron is taken by oxygen. So in next step, there it is CS3 C, CS3 C, CH3 CH3, then OH, and here is plus. Plus why? Because this bond is broken, H2O is formed, electron is taken, so therefore this is having plus charge carbon, which is known as carbocation. So first carbocation formation, then again this molecule is unstable. So how can it be stabilized? This can be stabilized because of this OH group. This lone pair of electron can be shared here, and because valency of carbon is 4, so if here a double bond is forming, it will become 5, very unstable, and it becomes then easy for this carbon to push this methyl group, and because this is requiring, so this methyl group will attach to this carbon. So here are two forces acting. Here is pushing this methyl group, push up methyl group by this carbon, and here is pull of methyl group by this carbon. So the effect is seen that CS3, because this carbon is gone, so this carbon will have now plus charge. OH double bond, here is shared electron, so double bond. Then here CS3 this OCS3 plus this CS3 attached to this carbon. Okay, Now what happened is that one to shift from one carbon, the methyl group, shifting to second carbon. First carbocation here, and here we are seeing here there is no carbocation. This is stable compound, but it is not that stable. You see here valency of oxygen is 3, this OH and these 2 bonds, so this is somewhat unstable. So, and we know that electronegativity of oxygen is more, so electron again can be pulled here by the oxygen, and a resonance structure is forming here, CS3 COH, then here CS3 CS3. Okay, here what is shown here, this is the resonance structure both. This is plus charge, how it is coming, this electron shared, so oxygen is here bearing 3 valency plus charge, again pulling to electron toward itself, making it neutral. But by doing so, the plus charge will develop on this carbon, because electron is shared, which is shared is taken back, so it will have plus charge. This is second carbocation. If you see here, this is the first carbocation and this is second carbocation. So 2 carbocations are forming. Now this can be stabilized. How? This can be stabilized by this, this way. Here if you see, this is a resonance structure, these are the resonance structures, and there is one more possibility for stabilization. Here this hydrogen bond can be broken, electron will be taken by oxygen, this H plus will liberate. Here the catalyst we used H2SO4, H plus took part here, and H plus is coming out, so it's acting as a catalyst. Here when this happens, then the product is forming, which is ketone known as Pinacol-Pinacolone. So this is Pinacol-Pinacolone forming. This is Pinacol-Pinacolone reaction or rearrangement mechanism. Here the point is that in first step there is H plus is attached, oxygen became positive, bond is broken, electron is on the oxygen, water formed, first carbocation formed, then one group migrated from adjacent carbon, then this is stabilized by this lone pair of electron of oxygens. That oxygen, they can have a resonance structure, but this resonance structure is not stable. Plus charge is there, here is plus charge, here is plus charge, so it is not that stable, but it is stable, quite stable. Sorry, it is stable, but it is not that stable, and it can be more stabilized by losing this OH hydrogen. This, by taking electron oxygen, the ketone will form. This is Pinacol-Pinacolone. So this